All right, line C4, learning test number 2. The first video that we looked at was going to be the effects of poor power quality, and we looked at a bunch of different things that it changes, heating and things like that. And now what we're going to do is we're going to go and take a look at what those possible causes might be. What is causing this to actually happen inside of our system? Inside of our system, we're going to go and have two main areas, once again, where we can go and develop poor quality from. One of them is going to be the supply side, external, that is going to be reflected in from somebody else out there who's creating bad power quality. The other one's going to be internal, where it's coming out of our own, and usually it is going to be coming out of our own system. We will start by taking a look at what supply side causes are going to be. That's going to be from BC Hydro or whoever you have that's supplying your power. That is going to go and be past your point of PCC, your point common connection, or basically where they connect onto our system itself. And they give you a list of a bunch of different things that can cause poor power quality coming from the outside. Lightning, wind, and other weather-related conditions that are going to be causing shorts to ground or shorts line to line that we are going to go and have, or massive amounts of voltage, lightning, that are going to basically be put onto it. Vehicular accidents involving utility poles or underground equipment, so that's going to, once again, shorts or line-to-line faults. Digging into underground cable, for sure it's going to be a short to ground as they go through it, but it's also going to possibly cause line-to-line. Tree branches, which are going to go and cause line-to-line or line-to-ground shorts. Animals contacting the equipment, once again, line to line or line to ground. Even bird strikes on top of a transformer. The transformer cans themselves are going to go and be shorted. Our transformer cans are going to be tied to ground, so we can go and short to ground whenever we get a bird or a squirrel that decides it's going to run across there. Equipment malfunctions, where the equipment itself was supposed to, prevent something from happening, but you get a switch that fails open or fails to ground or something like that. Vandalism, less commonly happen. People don't generally go around vandalizing high voltage substations because they know that chances are they're going to be that guy on the sticker that's bending over backwards with a lightning bolt going through it. Nobody wants to die on electricity, or just sometimes switching transients. All of these are going to go and be stuff that is going to come in from the supply side. Talking about lightning, lightning is massive. We're talking in the megavolts, mass amounts of voltage that are going to go and hit the line. And because in a lot of cases, you think about flat areas that are going to be prairie, farmland, things like that. Usually the tallest things around are going to be those power lines. And those power lines are going to be attractive. If they're going positive or negative, if it's going to be in the opposite direction as to what my lightning strike is, my lightning is going to be, attracted towards them. I've been a personal witness to a lightning strike that happened probably maybe 150 feet away from me to a utility. Took out the power to, the whole area and stuff like that. And you didn't so much hear the lightning strike as you felt it was like this massive concussive wave where you just kind of feel it inside of your chest as that thing just passes over. I was fine, I wasn't touching anything electrical. I happened to be just walking out towards my van at that point when the thing happened. But yeah, it was crazy the amount of power that was dissipated. And then the thing that I just remember seeing particularly was just the violence of the magnetic lines, and that lightning just happened. It was just seared in the back of my mind, seeing this bolt of lightning, feeling the sound wave just kind of pass right through me, but then watching the lines dancing. They were jiggling like they had been, and these are big, heavy overhead lines, from one of those big three-phase T-top poles that were just dancing around, and they slapped together. There was another subsequent spark, just from those lines slapping together. I guess it hit the one phase, then bounced, and then the way that the magnetic waves caused that thing to move, it was crazy, the amount of movement that you had out of heavy, heavy conductors. We get lightning fairly infrequently down here in the Fraser Valley. We get it more up in the mountains, but up in some of our more, prairie-ish types, particularly like North Fort St. John, areas like that, they get a lot more of it, and it's a lot flatter, so they get a lot more of these strikes. We do have surge arresters that are going to be placed on there. Surge arresters are going to be giant thyristors. I don't know if you remember the Diac. It's a giant Diac that they basically place on these, where they're going to have these, thyrites and lead discs that are designed to go and block voltage until they reach a point, and that point is then going to be usually anything that's going to be above whatever my supply line has, and then they're going to be able to short and divert that down to ground. These surge arresters are able to go and deal with a lightning strike when the lightning strike is going to be, a couple of poles away. minimum. If we get lightning that's going to strike over here, and we've got lines that are going through from pole to pole to pole like that, I'm going to be probably fine over here, but anything that's over here, even if I've got a surge arrestor that's going down to ground right over here, that's just a massive diac that's going to allow this thing to go and dissipate and drive down to ground, there's still going to be enough costs, enough other issues that are going to be present on the line for the lightning strike that I'll still feel it. But as I get further and further away from the lightning strike, it's going to attenuate. Remember that even single conductors have got inductance to them, and that inductance is a choke. It's going to go and slow that down. Capacitor bank switching is also going to go and cause issues. We have a lot of capacitor banks that are going to go and be used anytime that I'm needing to go and offset inductive loads. BC Hydro penalizes us and our customers for inductive loads, but they've got their own inductance on the system based upon all the transformers that they have on the system to go and transform different low and high values of voltage, as well as once again on those lines themselves as they go transmission line to transmission line all the way through. Each of those lines has got that inductance value. So every once in a while they're going to go and put on a capacitor bank, and those capacitor banks are designed to go and counteract that. Remember that if I've got a lagging power factor, I'm going to go and see where my voltage should be. If I've got a lagging power factor, my voltage is going to go and be down a little bit. And if I power factor correct it, I can bring that voltage back up to where I want this thing to go and be. BC Hydro is going to do this. They're going to go and use these. Now, sometimes they're going to go and have stuff like in industrial areas where during my workday, I get a lot more lagging power factors, so they got to bring the caps online. But at the end of the workday, everybody shuts down and goes home for the night. And then all of a sudden, they would be too high, right? You don't want to have overcapacitance because then you get an increase in your transformer terminal voltage, which is, once again, going to be bad for all of my systems. So they're going to switch those things on and off. Whenever they do switch these things on and off, there's going to be a really, really brief disturbance. Usually this is going to go and be less than one cycle. So that's a cycle over there, less than one cycle long that I'm going to go and see when I do switch these things on, but it is going to go and just give me ringing. Ringing is where this thing is, it's almost like a ringing noise. I don't know if you know or can hear that through what I'm trying to say here, but that ringing is going to go and cause, in some cases, multiple zero crossings. See how it drops down and hits that zero axis? It's going to be really, really rapid back and forth movements that is going to cause surges, because we're going to get a lot of expanding and collapsing fields, all those transformers that we have, etc. The other thing that does also happen with capacitor banks is when they switch these things on, remember that if my voltage is supposed to be here, then my voltage is sagging away. And if they've got an automatic capacitor that is supposed to go and bring that thing back up, because the lagging power factor is going to bring that thing back up, but it's going to take it a little bit before the transformer regulators are going to go and respond. Transformer voltage regulators change the taps or automatic tap changers that I'm going to go and have. So what I get is that I'm going to go and have my voltage might be sagging down, down, down. We're looking at just as a single line, but my RMS value of voltage that I have. So if my RMS voltage sags down long enough, then all of a sudden my cap is going to go and turn on. So here's going to be where my cap comes on. Cap on. It's going to bring it up, and it's going to have a certain amount of time that my transformer is going to be monitoring with its regulator, and its regulator is going to go and see when I bring this cap on. I'm going to bring that cap on just a little bit higher. The cap is going to bring us up to a certain amount of voltage, and there's going to be a certain amount of timing before BC Hydro's transformer is going to go and change taps, because that's a mechanical process, and we don't want to make a lot of mechanical, opens and closes. So if it sees that, we've brought this cap online and our voltage value is now too high for, too long, then it's going to go and change its transformer regulator, and then it's going to drop it back down to where it needs to go and be. Purpose of the cap is not to raise the voltage. The purpose of the cap is to go and deal with the power factor, but when it does deal with the power factor, it raises the voltage, so my regulator needs to go and switch over. So we get an over voltage that can last for a couple of minutes tops before my transformer regulators are going to go and change that bit. Line switching happens all the time as well. Line switching is, once again, BC Hydro works off of a grid, which means that if they have got lost to any sort of a section, maybe they're using this line to get through to here right now, and if this line were to go and get screwed up over here, what they would be able to do is they can go and switch in, they can go and send some power down here, they can take it down this one, they can switch it back up to here so that they can get it back to that load itself. They'll isolate that section, go out there, send a line crew out to fix what's going on, but in the meantime, they can bypass power around there until they get that line fixed up. Happens all the time. We will get small voltage transients, but usually they're not going to be nearly the same level as what we get with caps, because caps are going to be affecting us in our XL and XC, right? They're going to be changing so many system characteristics, where switching is just going to be reapplication of a timed in value of voltage that we're going to have. Our different types of interruptions are classed into three main classes whenever BC Hydro does have some sort of line switching, or whether it has, that somebody has, taken out a power line or something like that due to accident. They're going to go and have momentary, temporary, and sustained. And momentary is just going to be any time where I lose voltage for anywhere from half a cycle. So if I were to just lose this section over here all the way up to 3 seconds, we call that a momentary interrupt or momentary disruption. A temporary interruption is going to be anything greater than 3 seconds, but less than a minute. Oftentimes, these are going to be caused by bird strikes. We get a lot of birds that die on power lines every year because they sit on top of that transformer, and then they make contact from the transformer can over to the high voltage bushing with the wing when they go to, land or fly off or something like that. What we have on remote lines is BC Hydro will actually, instead of having to send a line crew out there, they know they got enough volts and power on the system that they can probably just blow that bird right off of it through arcs. And so they're going to have these reclosers that a bird, lands on top of that can. If I take a look at, here's my can with my high voltage bushing off of that. You get that bird that lands over there. I'm going to do a terrible job of drawing a bird over here. It's got little winglings. Winglings make contact over there to the high voltage line while its feet are on the grounded can, and it's going to usually just blow that wing right off the bird. You'll find these things in separate plate pieces, but it's going to trip the overcurrent. And what BC Hydro will do is they're going to have a recloser that's going to try on a lot of lines up to 3 times to just reclose. It says, boom, it's going to send power out and has it blown it off of that line, etc. So you're going to go and have these temporary interruptions that are going to be happening while the reclosers try to go and blow that off of the line. Sometimes you're going to get a little bit of surge, a little bit of transient that's going to happen as well. Sustained interruptions is just going to be anything that is going to be more than 1 minute. They call that a sustained interruption. A sustained interruption is where the power was designed to go out, but then they lost the power. Something interrupted it. Vehicles, trees, ice storms, anything like that is going to be an interruption. A blackout is going to be a planned one where they have to go and, take power down, but that's going to be something where it's going to be a sustained interruption, but they're choosing to go and do that, so they're just going to go and black out that area because they have to do service or maintenance or, build or paralleling lines or things like that. Under voltages, commonly called brownouts, are going to be when we have too little voltage on the system. If we get a lot of demand on the system, we know that we have got V is equal to IR, right? So anytime that I get a lot of current that is going to be dragged through my system, I'm going to drop a lot of volts across from point to point inside of my system. Therefore, what I'm left with, if this is where I'm feeding power in, because I drop a lot of volts across this line section, I'm going to have less volts over here, and then I'm going to have less volts over here if I've got, different consumers that are taking taps off of these ones. We are supposed to be at plus or minus 5% that we are going to go and have for our value of voltage. So you just do the math off of the type of system that you are going to go and have. But it should not be, very far away past that. You can go past that, then you're going to go and deal with undervoltage, commonly known as brownouts. Brownouts do sometimes happen just as a result of short-term operation rather than just, long-term. So if you got a motor that starts up at one facility, particularly if it's a massive couple hundred horse motor, it can brown out, the whole grid just in that area until that motor comes up to speed due to the amount of inrush current that we're seeing off of that. Otherwise, it is very common that we are going to go and see our value of voltage dropping starting at about 8 in the morning once we start bringing people into work, powering up equipment, etc. Voltage overall is going to go and drop, and it's usually going to drop to its lowest right about 3-4 o'clock when we still have industry going, but we also have people starting to fire stuff up for supper. Stoves are going on and things like that. Kids are coming back from school, turning on, computers, video games, and things. All of that is going to go and give us our lowest peak, usually in about that 4 o'clock, and then after that, our voltage starts coming back up again. If I do have under voltage, it's going to go and usually cause equipment to go and shut down. A lot of my critical equipment is going to go and have under voltage protection. That is going to say the voltage is too low. Rather than me cooking stuff off here, we'll just go and shut it down. Causes of the under voltage, though, usually is going to be current through there. Sometimes it can be these other ones that they talk about, loose or corroded connections, or inside of your own facility, unbalanced phase loading connections, where you had, somebody that decided they were going to take all the heaters in the entire plant off of phase 1 or something like that. Sag is not going to be complete interruption of power. So in other words, it does not go all the way down to a value of 0. It is just going to go down to a low value, right? We have interruptions, which go down to 0 voltage. We have under voltage, which is going to be, below that 5% level that we're going to have. And then we're going to go and have sag. That is going to be a temporary drop below 90%. In other words, we're going to have a 10% drop that's going to go and happen. But it happens anywhere from half of a cycle, just one alternation, all the way up to a minute. Sags, because they are so short, are generally speaking going to be harder to go and track down. If you have a sag, your customer says, yeah, once or twice a day stuff is happening, ask them to document what's happening in their facility. If there's nothing that corresponds, that they've got a big freezer that's coming on with a massive hermetic pump or things like that. If they can't document something that's happening inside of their own location that would be causing that sag, then ask them to kind of watch what's going on at neighboring industrial sites. Is the neighboring one always kicking on a massive conveyor or something like that? Voltage sags oftentimes are going to be significant enough because it's going to be just a rapid drop in voltage, usually due to massive motors starting up, that we're going to go and kick out a lot of our computerized systems. They're designed with a safety that if the voltage gets too low, they kick off, so they're just going to respond and shut themselves off. But VFDs and adjustable speed drives are also going to be designed with the same thing. They're going to go and shut down because they don't want to have a low DC bus link that we are going to go and have. Other types of electromechanical components that are going to be held in magnetically. If I lose my value of voltage over here, if it drops too much, contactors, remember they got that spring inside that's trying to push that armature back out of there. If we lose this voltage, we're going to go and lose magnetic flux, which in some cases is going to be enough that those contactors are going to be able to release and go back. Usually you can go and attenuate this by taking care of your large motors. All of those reduced voltage starters that we took a look at, auto transformer startings, we did wide delta startings, we did impedance startings, anything that's going to give us a reduced voltage is going to go and slow this down. Or if you go with a soft start for an adjustable speed drive, rather than just connecting across line to line and allowing this to drop, bring your motors on slow. Usually this stuff is going to go away. If you do have sag you can't get rid of, then find the things that it's affecting, particularly computers, etc., and put those on to uninterruptible power supply so that they are not affected by it. Over voltage is when I get too much voltage, more than 10% for a period of more than 1 minute. Remember, anything shorter than that is going to be like in my transients that are swells that I'm going to go and take a look at. Over voltage is going to be sustained amount of too much voltage. Usually it's going to be based off of the utility at that point. We don't commonly cause our own over voltages, but if that utility was overcorrecting because they had a bunch of inductive loads and then somebody else shuts off their plant for whatever reason, all of a sudden you could be left with way too much voltage on that. It's going to go and exist on your system until the tap changers at wherever BC Hydro has got their near switch yard react and go and shut that down. Voltage swell is going to go and be a large amount of voltage that's going to happen for a short amount of time. Okay, over voltage is when we get too much for just a long period of time, over top of a minute. Swell, or what we commonly call a surge, anywhere from 110 to 180% for a short amount of time. Half of a cycle, all the way out to up to 1 minute that we're going to go and have. All sorts of things that can go and cause it. On delta systems, one of the most common causes is where I'm going to go and have a single line ground. That's going to go and happen. As soon as I ground a single corner of a delta, that's fine. Remember, any system can be grounded at least or only one time. So normally we know that the ground exists theoretically at the center of a delta type of system. Right? All the voltages are going to go and balance around it. Nature tends to want to go and balance. But as soon as I ground one of these systems, that's just going to move that ground over. Now we're physically attached to here, not because I necessarily did it on purpose, but because I've got a line that's making contact or a car accident or something like that. And as a result now, this line over here, which, maybe this was a 600 volt delta, now this point is sitting at 600 volts above ground. Same with this one over here is going to be sitting at 600 volts above ground, whereas before they were all just hovering 347 volts above ground, but we see it's a massive amount of voltage. Note how they said it's 180% of nominal. That 180% of nominal is based off of 173%, which would be what I would have normally for a rise that would come from, one of these. Voltage swells are going to be rapid, and sometimes they're so rapid you don't actually see them happen, but you just end up with a bunch of dead equipment off of that. Our undervoltages, sags, things like that, we notice them because stuff kind of browns out and shuts down, but these ones here, all of a sudden something boom happens and you get a bunch of dead equipment, so in a lot of cases we just attribute it to those surges. Voltage fluctuations are just going to go and be when the voltage itself is changing, going a little bit high, going a little bit low, etc. Inside of there can be caused by all sorts of things. Usually it's just going to be when they're doing switching out there, or where they have got certain types of loads that are connected that have got a cyclical type of cycle or cyclical type of operation, where it's going to pull current, then it's not going to pull current, then it's going to pull current, then it's not going to pull current, then it's going to pull current, then it's not going to pull current. They give the example of arc furnaces, where we are going to be establishing and shutting off arcs, to go and create massive amounts of heat. Those type of loads are going to go and give us voltage fluctuations. Usually what you can do is you can actually kind of time out these things. You can watch those values of voltage, and if you start to track this and you see that it's following an actual regulated cycle, you can usually track it down to your facility or a facility next door that has got, certain problems or certain operational systems that are going to be following that. Okay, let's talk about transients next. Before we actually go into what the transients are, though, let's talk about what the difference is between a transient and a voltage swell. A voltage swell, we'll go back to this one over here, has to take place for at least half of a cycle, right? That we need this thing to go and happen on. If it doesn't take place for at least half of a cycle, if this thing drops back down to its regular value of voltage, so this would be a voltage swell or a surge that we would have through here. This would be a transient, where it goes and then it returns to its original waveform over here. Because we see that the weirdness that we have on the wave, that's this section over here, does not exist for at least that half cycle. If it exists for that half cycle, we can go and call this thing a surge or a swell that we are going to go and have. But if it's lasting for less than for a half of a cycle, then we're dealing with what's called a transient. They're going to be sudden peak events. Now, we do oftentimes go and use the same terminology. Remember how a voltage swell is sometimes referred to as a surge? We can also refer to impulse transients as being surges that are going to happen inside the system. Neither of those is correct. It's just kind of a common way that we mangle the English language as we're talking about these things. These ones here are going to be sudden peak events that are going to go and happen as a result of switching inside of our systems over here. There's a couple of places that really cause these ones inside of there. Oscillatory ones are going to be ones where it's going to go and happen all the time. It's going to oscillate back and forth. We're going to also have single ones that are going to happen just once in a blue moon. Places that cause this are things that are going to go and cause this are going to be things like drives that are going to go and cause these really sudden short things as we're kicking on. I don't know if you remember, but those square waveforms that we see inside of our drives, we start to go and kick on, and so we're going to go and have sudden amounts of current that are going to go through. The other place that really gets causes this is LED lighting. Particularly if my entire facility is lit with the exact same type of fixture from the exact same manufacturer. And this makes sense, that you want to have that so that you've got fewer spare parts you need to go and keep around. But what we get is we get that peak repetitive stress or peak repetitive current that is going to go and happen inside of a LED, where an LED, when it's turned on, we see very little, and then all of a sudden it's going to go boom. We're going to go and get a massive, but only for a fraction of a second, amount of current, and then boom, it goes through in the opposite. Boom. So this red line that I'm drawing over here is going to go and be my LED, peak repetitive stress that I'm seeing over here. That peak repetitive stress is then going to get added onto whatever I have for my other current. That's going to be this green waveform that I'm going to have over here. And the result of that is going to be that now I'm going to go and end up with these transients. The beautiful thing is that I see that it's a consistent transient. As soon as it's consistent, it's got it's something that I can go and track down relatively easy. It's the inconsistent stuff that's always harder to track down. Oscillatory transient is one where it's going to oscillate back and forth, where it's going to go and change either the voltage or the current. The voltage can be the same, but we get that surge of current that's going to go and run through. These over here are going to go and be my oscillatory transients that I'm going to go and have. These ones over here were incorrectly identified as being oscillatory transients. These are supposed to be impulse transients. Impulse transients happen only just kind of once. Oscillatory are going to oscillate back up in the positive, down to the negative, up in the positive, down to the negative. So just relabel those two, switch them around. These are going to go and happen, the oscillatory ones, oftentimes when I have got either inductive or capacitive loads, or when I have got current that I'm only letting through at a certain amount of time. And they're always going to, if we've got oscillation, oscillation refers to back and forth movement, like a pendulum. And we see that often here. We get a pendulum high, pendulum low, or pendulum in the positive, pendulum into the negative, pendulum into the positive, pendulum into the negative, etc. as we're going back and forth through these. Oftentimes they're going to be caused by, we've said the LEDs, and we went through that. Other times by the drives that we are going to go and have. Adjustable speed drives in a lot of cases are going to convert to DC, right? If I have got a converter so that I can run either DC motors or so that I can go and run VFDs, we're going to have that DC link on the inside. And anytime that I'm going to go and have current that's going to be switched in once in a while, and that's really what we're happening, right? If you take a look at it, we know that my waveform, if we go and have that DC bus, we're going to go and filter that. And so what we actually have, let's draw out a full three-phase waveform like this, is we are going to go and have this waveform. Right now, that waveform is going to go and be supplying power, and then it shuts off. And then the next waveform is going to be supplying power, and then it shuts off. Only when it crosses, when we're doing our line-to-line rectification, when we cross that line, do we actually go and pass current. So this phase right now delivers no current, no current, no current. So I'm just going to go and follow that through. It's delivering no current, no current. And then all of a sudden, boom, it is going to go and deliver current. And then voltage gets picked up by the next phase, and so that phase shuts off. Nothing, nothing, nothing. And then boom, it's going to go and deliver again. So we're going to go get these, oscillations where it's going to go and have nothing, and then it's going to pass a bunch, and then it's going to have nothing, it's going to pass a bunch. And every time that we get that rush of current that's going to go and happen as we're going through our converter, then we're going to have that same rush of current that's going through everything else that's upstream, transformers and things like that. And that's really where we're going to get that oscillation. What we want to do is we want to go and stick reactors ahead of the DC section of our drives, ahead of the DC link. So any place that we have got our converters, where we are going to go and convert from our AC into our DC, then we want to go and have reactors that are then going to be able to go and store energy in those magnetic fields, and then they're going to keep that oscillation inside of the drive. Most cases, you can buy your drives with reactors on there. When in doubt, buy the reactor, okay? You would much rather spend that little bit of extra money right now, take it out of your profit margin, than have to go back for warranty call after warranty call after warranty call. DC offset happens inside of a system. Oops, sorry, that's the wrong one there. DC offset happens where I go and shift my neutral plane, and I can shift that by having rectification that goes wrong. Over here, I should have my neutral plane right over there, but we see this one here has been shifted down, right? Half that waveform and half that waveform, instead of them staying like that, we've got a negative DC offset, which is bringing our waveform shorter on the positive side and taller on the negative. Over here, I've got a positive DC offset where that neutral plane has been shifted as well. Usually, it is going to go and be failure of DC rectification that is going to go and cause that, where that gets put back onto the line itself. It can cause some massive problems with saturation, where I'm going to go and have clipping of my waveforms, where I can't pass those tops of those waveforms all the way through, because transformer magnetic cores are going to go and be saturated at that point. So I'm going to go and get weird voltages. My voltage over here is going to get up to a certain level. My transformer is going to be ridiculously hot, but I'm going to have a weird waveform that's going to be coming out of where it's flattened on one side or another. Noise is usually going to be caused by arcing that we're going to have on the system. Noise is not going to be classifiable as being anything. It's just going to be this jaggedy, nasty, nasty looking line that we see changing magnitude, direction, back and forth all the time inside of here. Arcing gives us this. If you see consistent noise on the line there, it's usually because we're going to go and have consistent arcing. We know about AFCIs on residential systems that are designed to go and monitor and look for this type of a waveform and kick out. Industrial systems, we're able to go and have arc fault detection as well. They're just going to do it through CTs that they're going to place around the line, and they're going to be looking for amplification of these type of systems so they can go and kick those things out. Frequency fluctuations, this is not very commonly going to be coming in from BC Hydro. BC Hydro, if they have got frequency fluctuations, they're getting penalties out the nose. So they're just going to prevent that from happening. Usually it's going to be if I am trying to go and synchronize with BC Hydro. We get a lot of cogen sites that are going to be involved inside of some of our lumber processing, where we're going to go and take all of the bark and the branches and the little offcuts and stuff like that, and we are going to go and burn that stuff inside of these huge furnaces, use those furnaces to go and heat steam, and then run that steam as steam turbines. And what we'll do is we are going to go and have BC Hydro that's coming into our facility, and then we are going to go and have our cogen that is going to be just a generator that is going to go and synchronize with that BC Hydro, and it's supposed to go and help supply some of that power. So that anytime that the cogen is not able to go and carry enough power, then we take the rest off BC Hydro, and anytime that BC Hydro isn't needed, we should be supplying everything through the cogen path that we're going to have off that. If I don't have good regulation on my generation over here, that this generator itself doesn't have very good speed load characteristics, etc., then I'm going to go and get frequency fluctuations that are going to go and have. Usually it's the local system, not BC Hydro's system. If BC Hydro does have a frequency fluctuation, it's going to be happening, more or less across like entire towns and cities and stuff like that. Erratic operation of anything that is going to be computerized, once again, or that is going to be transmitting data, because data is going to be based off of timing. Everybody takes their turn to speak, and all of a sudden we throw that all out of whack right over here. Notching is going to be the opposite to my transients, right? We took a look, we saw that we had our oscillatory transients. This was the oscillating oscillatory transients, where we saw those peaks that were coming out of there. Notching is going to go and be where we're cutting away small amounts out of each one. These are going to be caused by where we get some sort of an inrush on the system. This is going to be something that we see usually on the voltage system, because V is equal to I times R. So if I get a rush of current, anytime that I get a current waveform like this, if I get oscillatory current that looks like this, it is usually going to go and result in voltage notching that is going to go and look like this. Because that current, every time that we get that current spike, we're going to get a small amount of voltage drop that we are going to go and have. So we get just this, this waveform that's going to go and look like that. It's going to go and cause problems, but they're so closely tied together. The current waveform spiking as the voltage comes down, we just treat it as one problem usually. Internal power factor problems that we can go and have inside of our plant are going to be usually caused by our harmonics that we are going to have inside of the system. And harmonics are going to screw the waveform over. This is what a good waveform, what I'm drawing here is what a good AC waveform, let me try and redraw that because that didn't look very good. It's what a good AC waveform is supposed to go and look like. Now, I'm able to go and get harmonics. We're going to call this first one over here our fundamental frequency, or our 1th harmonic, okay? It's going to be number 1 because it is the best, the fundamental. It's going to be at 60 hertz. If I get a harmonic, harmonics are just going to be multiples of that. My second harmonic is going to be 120. My third is going to be 3 times 180. My fourth is going to be 4 times 60, 240. Let's go and take a look at what happens when we go and add in a third order harmonic over here. A third order harmonic is going to go and be 180 hertz that we're going to have. In other words, we're going to go through 3 of these in the same cycle as we would go and have 1 of these over here. So if I were to break this down into thirds, that's going to be, thirds for that waveform. My harmonic that I'm going to go and have is going to look like this. Let me try that one more time there. It's 1, 2, 3, like that. So this blue one here is my 180, this red one here is my 60, and what we get then is we are going to go and get addition or adding of our values of voltages that are going to be together. Now I did draw this red one here much larger so we can see it across the top. The red one should actually be lower for it to work out to become this type of thing that we're looking at here. Like that. What we see over here is that as I have got both of these positive, they add together. So we're getting that bump that we're getting on this side over here. I'm just going to draw it a little bit higher. Then right over here, this one goes negative. Well, this one goes positive. So the positive and negative add together, and we are getting that notch. And then right over here, this one goes back to being positive. Well, this one's still positive. So we get that one over there. And then we're going to go to the negative side where we see both negatives. So they hump together. And then we're going to see a positive and negative. So they're going to go and notch together. Then we're going to go and see that these two are going to go and hump together over here as well. So we create these humps that are going to be on here. It's going to be called a double hump waveform that we see over here. And it's a classic sign of us having third order harmonics on that system, where we lose that top of the peak. And this, instead of us being the regular slope, this gets more steep. More steep is always going to be a problem because dV dt, right? We got that rise in voltage over top of rise in time. There's so much stuff that is going to be caused, our issues that we're going to go and see out of these. We get third order harmonics that are going to go and happen out of so many different types of systems, but particularly they're going to happen out of what we refer to as non-linear loads. Non-linear loads are where we're not taking current from these things all the time. That same thing that we just talked about before, where we have got our A phase. Right now we see A phase is going to be, if I'm rectifying power, A phase carries, and then nothing happens, then A phase carries power again. And then, B and C are going to go and take over, then A phase, then B and C, etc. So if I take a look at it, my current waveform for A is going to be, anytime that A is carrying power, we're going to go and get a blip, and then we're going to get nothing for our current from A, and then we're going to get a blip, and nothing for current from A. It is not linear, right? We're not seeing a consistent amount of current that's going to be happening all the time through here. We're only seeing it in a single direction. We're not seeing it go through on this side, right? We've completely lost that waveform that we have over here. As a result of that, we're getting this little blip of current that's going through there, and then this is going to get even further exacerbated or, cause problems by the fact that we're going to go and have this cap that we are going to go and have. Because the cap is going to go and carry current through in a lot of cases, which means that now instead of us taking current the whole time, right now we've got that cap that was charged up that was carrying through, so now all of a sudden we're going to get a more compacted and a sharper wave that's going to go and happen, where we would normally have, that longer wave. This is going to go and now start to go and cause echoes inside of our system. And those echoes are just going to be what we refer to as being our harmonics off of that system over here. We see that this current pulse that I'm getting over here comes off of my fundamental. But now that current pulse is going to go and decay through other stuff. It's going to decay through caps on the system. It's going to decay through transformer quantities, all sorts of different things. And so what we'll get is we're going to go and get these different types of harmonics that are going to go and happen off of these. Over here, we're going to go and take a look at a table that we have of harmonics. And we're going to go through some really, really important stuff. First thing we're going to go through is our fundamental. Okay, we're going to start right here.